measure the length or weight of an object, we note the measurement in the form of numbers. Here's a brick. Let's measure its length. Observe that the length is between 15.4 centimeters and 15.5 centimeters. Since we are not sure, we can say that the length is approximately 15.45 centimeters. In this measurement, 1 and 5 in the whole part and 4 in the decimal part are certain, while the 5 in the decimal part is uncertain. This 5 is uncertain because this is an approximate value. The values of many measurements in real life are decimal numbers. Digits in decimal numbers can be categorized as certain and uncertain. The number of digits in a measurement which are certain plus one additional digit which is uncertain are together known as significant figures. There are rules to determine the significant figures in a given number. The first rule says that in any measurement, all non-zero digits are significant. For example, we weighed a bar of steel that measures around 62.45 kilograms. Here, all the digits are non-zero numbers. In this number, all the 4 digits are significant figures. The second rule says that in any measurement, all the digits including zeros are significant for a decimal number greater than 1. Here, we have the length of a water hose which measures 6.407 meters. This number is greater than 1. There are 4 significant figures in this number. The third rule let us take the constant of the zeros to the right of the decimal point, but left to the first non-zero digit are non-significant figures. Consider any number. Say 0.006452. Observe that there are 2 zeros between the decimal point and the first non-zero digit, that is 6. These zeros are non-significant figures. Hence, the significant figures in this number are 6, 4, 5, and 2. Therefore, the number of significant figures is 4. The fourth rule states that if the measurement is a whole number, then the case becomes ambiguous if there are zeros to the left of an understood decimal point, but to the right of a non-zero digit. To remove this ambiguity, the number should be reported in scientific notation. That is, a into 10 raised to power b. For example, let's take a number 2507000. This is a whole number. According to rule number 1, there are 7 significant digits in this number. However, in this number, there is an understood decimal point, which is usually not written. The rightmost non-zero digit in the number is 7. There are 3 zeros between the 7 and the understood decimal point. We can report this in scientific notation as 2.507 into 10 raised to power 6. Now, the number of significant figures in this number is 4, since 2.507 is greater than 1. The fifth rule says that in any measurement, all the final zeros in a decimal number obtained by rounding off a decimal to a given number of decimal places are significant. For example, let's take the number 9.8982. There are 5 significant figures in this number. Let's round off the number to 2 decimal places. The resultant number 9.90 has the digit 0. But this number is greater than 1. Therefore, 0 is also a significant number. The number of significant figures in this number is 3. Using the rules we just studied, decimal numbers can be rounded off to the required significant figures. There are certain rules to round off the uncertain digits in a given number. The rule by convention says that the preceding digit is raised by 1 if the insignificant digit to be dropped is more than 5, and is unchanged if the latter is less than 5. Here is an example. We will round off 8.917 to 3 significant figures. This number has non-zero digits and there are 4 significant figures. In the decimal place, we will round off 7, resulting in the number 8.92. Here is another example. Round off 7.9342 to 4 significant figures. This number has non-zero digits and there are 5 significant figures. In the decimal place, we will round off 2, resulting in the number 7.934 as the number to be dropped, which is 2 is less than 5. Now, consider 2 numbers 3.945 and 3.975. Let us round them off to 3 significant digits. In this case, the insignificant digit to be dropped is neither greater than nor less than, but is equal to 5 in both the given numbers. To do this, we have another convention, which states that if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. Thus, the answers are 3.94 and 3.98 for the rounded off numbers as shown. Here, the length can be written as 8.1 plus or minus 0.1 or 8.1 plus or minus 1.2%. And the breadth can be written as 5.1 plus or minus 0.1 or 5.1 plus or minus 2%. Hence, using the combination of errors rule, the area of the field calculated as the product of these 2 quantities would be 41.31 plus or minus 3.2% or 41.31 plus or minus 1.3 square meters. We can report this as 41 plus or minus 1 meter square. Here, 1 square meter is the error in the result. Thus, the result also has 2 significant digits, which is same as the original data. Rule number 2 says that the relative error of a value of a number specified to significant figures depends not only on n but also on the number itself. If there are 2 quantities, say 10.01 meters and 80.5 meters, both carrying an error of 0.1 meter, then the relative error in 10.01 meters is plus or minus 1%, while the same for 80.5 meters is 0.12%. Another important point to remember with significant figures is that intermediate results in a multi-step calculation should be taken to an additional significant figure in every measurement than the number of digits in the least precise measurement. Consider a number, say 6.55. The reciprocal of 6.55 taken to the same number of significant digits, that is, 3, is 0.152. However, the reciprocal of 0.152 is 6.58, which does not match the original data we had. Now, if we consider the reciprocal of 6.55 to 4 significant digits, we get 0.1527. The reciprocal of 0.1527 taken to 3 significant digits is equal to 6.55, which is the original data again. We learnt earlier about